Hello. Welcome to Relevant Logic's presentation about indexes. I call indexes the second pillar of database wisdom because schema design is clearly the most important. The other is queries, but I think indexes in some sense come before queries because although you tend to design indexes and queries together, it is generally much easier to change queries than to change indexes. In that sense, you design the three in the order schema, indexes, queries. My name is Gyron Howe. I am the President and CEO of Relevant Logic, and I've been working with all the major databases for 15 or 20 years now. In my experience, despite the central position of the database in most business applications, many developers are not familiar with the subtleties of index design. In fact, index design is an issue almost as deep and complex as schema design itself and warrants just as much attention. If you aren't aware of the subtleties that make this so, then I can say that virtually always, learning the major constraints and possibilities that indexes entail will make your applications both more responsive and easier to maintain. Because this talk is long enough as it is, I have decided not to include the discussion of related issues such as testing queries or using the explain feature of your database. This last is particularly important and relevant to indexing, but a proper discussion of it would require another similar length presentation. Suffice to say that if you use a database, you must be familiar with the output of the explain command so you know how the database is executing your queries. You must understand how to use explain to analyze how the database is executing your queries before you can help it to either execute the method it is using faster by providing helpful indexes, or perhaps you can lead the database to choose a faster strategy entirely by providing it with a better alternative through indexes. I am no fan of MySQL. It would be a marvelous technology if it was the only SQL database available, but many alternatives are available, and MySQL is worse than every alternative SQL database, essentially in every way. In particular, it is in my experience slower and less reliable than the admirable PostgreSQL, while having many fewer features. Many folks are not aware that there may also be licensing issues for use of the open source license of MySQL in some applications. MySQL is particularly weak in its indexing features. So that I don't need to keep saying, MySQL doesn't support this, I will instead display this symbol on the slide when I'm discussing any feature MySQL doesn't support. Here is a list of the most important things everyone knows about indexes. They trade more insert and perhaps update and delete time, and more storage space for faster queries. I won't belabor the issue, but it is a most important one. It is reasonably accurate to say that you can divide your database's insert speed by the number of indexes on the table plus 1. For this reason, you should not have any indexes that you are not using. You'd be surprised how often this happens. And you should have the fewest, most effective indexes you can. Obviously, how you weigh this consideration depends on the balance of updates to queries in your particular application. Here is a list of more things that folks know about databases. Or rather, it is a list of things that folks believe about databases that are anywhere from false sometimes to just nonsense. It is an almost universal belief that all foreign keys should be indexed. Another common practice is to have an index on every single field that is commonly searched. Folks also believe that indexes become stale or unbalanced or some other such thing, and that the database will benefit from rebuilding its indexes regularly. I will not comment on this further other than to note that the B-tree data structure that is used for indexes is very efficient and self-balancing, and unless it has become corrupted, rebuilding an index will have no noticeable effect. Folks that are aware of the value of compound indexes usually believe that the predicates in an index should always be in order of selectivity. Folks that are familiar with the use of prepared queries or bound queries almost always believe that such queries are always faster than dynamic queries, meaning queries with inlined values that do not benefit from query plan caching. While this is true much of the time, there are important cases where the dynamic SQL will in fact be faster. And finally, folks often believe that a faster computer will solve their query time problems. In fact, however, many queries are dominated by seek times, which are hardly changed by RAID arrays and faster CPUs. A faster machine will be able to handle a greater simultaneous load, but many or most individual queries will not run much faster. Much of how we do what we do in computer programming is because of the reality it presented in this and the next diagram. Here we see the different amount of time required to access a level 1 cache on a CPU compared to the time required to access main memory. Note that there is about a 100 times slowdown for the CPU to go to main memory. But note that we can access main memory 100 times in the same time as we can do a single green block on the next slide. So we can access main memory 100 times and level 1 cache 10,000 times in the time it takes to access a single byte from an SSD. But this is nothing compared to the hundreds of times slower seek on an old-fashioned hard drive. An important thing to note here is that the time a hard drive can do a single head seek, it can read about 2 megabytes of contiguous data. If every record is 1,000 bytes, we can read 2,000 records in the time it takes to do a single disk seek. Now, in order to read the data, there is a certain minimum amount of sequential reading that must take place in order to get the data into RAM from the hard drive where it can be processed at a reasonable speed. Beyond that, it is the principal challenge of the database server to find an efficient balance of disk seeks and more sequential disk reads in order to do the reads we actually want in the shortest amount of time. It might seem, particularly from this diagram, that SSDs might be the savior of database speed, but in fact SSDs are not in general suitable for most database applications. This is because they wear out and fail catastrophically after a surprisingly small number of writes. So you can have a database server that is ridiculously fast for a few months, at which point it will suddenly fail completely and without warning. A much better strategy for most folks is a hard drive and then enough RAM on the database server that it can have all the important records in cache. This would solve most folks' problems immediately, but I've never actually worked anywhere that could do that. It always seems that a business that can afford a beefy server with 64 gigabytes of RAM and a RAID array is always a business that has more data than that. Thus, in homage to my massive ego, I have coined Howe's law. Businesses can never afford the servers they really need. The corollary is that your database is never fast enough, which I guess is why you're interested in this presentation. Some notes about queries. A query is not usually a computer program. When you give a SQL Server a query, you're asking it to construct a program to find the data you want. In doing this, it tries to balance random and sequential I/O, as we've already discussed, as well as CPU time and memory use. Note that finding an efficient way of resolving a query is what is known as an NP-hard problem, meaning it grows very quickly with the complexity of the query. Note, for example, that the server joins 2 tables at a time. If you ask it to join 7 tables, there are 720 different join orders alone to consider. Add in that there are possibly 3 different ways of doing each of these joins, and then all the possibilities for which index to use and so on for your where clauses, and you can see how a query can easily get into the millions of possible solutions. A note on logically complex queries. Applications that use a database backend mostly issue queries with where conditions that are joined together with AND. Most often, when you have OR as part of your query, you can convert the query into what is effectively a union of 2 or more queries which contain no OR conditions. The logical conditions in a where clause can be arbitrarily complex, though, and it is impossible for me to give general advice about more complex situations. So when you're considering the case where you can treat a query with OR conditions as equivalent to a union of queries with AND conditions, then you can try and optimize those separate AND queries by themselves. But the advice I'll be giving here mostly applies to where clauses in which parts are joined by AND. If you have a query which involves a complex web of where clauses involving OR parts, you can try to employ the sorts of techniques I'm discussing in this presentation to make parts of it faster, as you see when you do an explain, but this case may be one in which you should stick some to smaller, simpler indexes. Now to some detail about how the usual B-tree type of index works. In discussion of data structures like this, you will hear talk of pointers and addresses. They amount to the same thing. A B-tree is a set of blocks of values with attached addresses of other blocks, or of one or more actual records. That's what the arrows indicate in this diagram. Each of these blocks will be in a single place on disk, but each of the arrows in the diagram usually will require a disk seek to a different location on disk. If you look at how the pointers and the things they point to relate to one another, we have a pointer to the block whose values are all lowest under this block, then a value which gives the lowest value in the next block under this block, and so on. The last set of blocks has pointers to a list of pointers where actual values are in what is called the heap. You may wish to pause the presentation at this point and stare at the diagram until you see how it is constructed. It is important to understand this if you're to work with databases effectively. The heap is just a list of the actual records in our table in a random order. Notice that there are quite a few disk seeks to access a single record. Notice also that there are not a whole lot more to access further records in the order provided by the index. But bear in mind what we saw about the speed of just reading records straight from the heap versus these disk seeks. Just reading through a file is a surprisingly fast operation, so we should not be too surprised to note that quite often, although we think we have provided the database with a useful index, it will decide to ignore the index and just chew through the records on the disk instead. I should also note that indexes are a shallow structure. A very large database might have 4 levels of index. Something that was massive might have 5, and if you're Google you might get to 6 or maybe even 7. But in general, finding an entry using an index in your database will involve 3 or 4 disk seeks at most. Now that we have some idea what an index looks like, we'll start to discuss how to get the most effective indexes we can. We can go a long way with a simple to understand metaphor in which we imagine our table as a kind of book. We imagine that we are in some sort of post-apocalyptic scenario and we want to make a list of employees of our company using a very old-fashioned sort of printing press. Because setting the pages takes a lot of work, we just reuse last year's plates for the main contents of the book, taking out and inserting new records as needed wherever we can. So our actual list with all the details of the employees is in an entirely random order. This is plainly a pretty difficult sort of thing to work with, and since there are so many of them now unemployed in our post-apocalyptic world, we consult a programmer who ought to be an expert on organising information, right? Our expert advises us to add an index for each field we want to search on. Following his advice, we add an index for family names, showing the page and row numbers on which each name appears. We call the field family name, by the way, rather than last name, because Jacob points out that last name is actually ambiguous, because if someone is Chinese, do we use their actual last name, which is their given name, or do we use their family name, which is their first name? And how do we get data entry operators to do that consistently? So this is clearly great and very useful, but we feel it could be better. If we wish to locate information about Steve Simpson, for example, I can find Simpson pretty easily in my index, but there might be 50 Simpsons in our company, so now I have to still look through a lot of pages to find the person I'm looking for. And what if we want to find who works in a particular branch? We often need to know that, and this index is of no value for that at all. So we go back to Jacob and we ask him about this, and he makes that sound and emphasizes that he'd said we should add an index for each thing we search on. So we should also have indexes on first name and branch. So we add the given names, not first names, index, and we sort of squint at it a bit. We can now find Steve Simpson more easily, but we still have to do this thing where we open both indexes to the relevant page and look through the two lists for the matching page and entry value. When you ask a computer to do a search that needs to use 2 separate indexes, it can do something pretty similar. It builds an array of bits in memory with 1 bit for each matching table entry, does that for both indexes, and then combines the two using a fast bit operation. This is reasonably efficient, but as we will see, you can usually do better. Next we add the branch index. That's not really very useful at all. Looking to do better, we fire Jacob, we find another programmer, Gwen. And Gwen tells us that rather than having all these separate indexes on separate fields, we should have a single index that includes all the things we want to search on. This sounds like exactly what we're looking for, so we add a single index with branch and family name and given name, and then we go back to Gwen because this isn't quite right. Now Gwen adds some more information to her instructions, which frankly she might have given us the first time, and she tells us to order the index according to how often we search on things. Now this is more like it. Finding Steve Simpson is now easy. But hang on, while this index is quite effective, it is of no use in finding all the staff at a particular branch. Gwen thinks of something else that she didn't mention that first time and gives us permission to have multiple indexes. Now we can have a separate index that puts branch first, and we're actually pretty happy. So our first and most important lesson is that we should usually prefer compound indexes over indexes on single fields. It is very little extra effort for the database to maintain an index with more fields. It works just as well for searching on the first field in the index, but we can also use it to search on other fields. This isn't to say that it isn't a bit slower to maintain such an index, mostly because it takes up more RAM and disk space which has to be shoveled about. So you shouldn't just have enormous wide indexes for no good reason. Thinking we no longer need Gwen's advice, we now go off and make an index on whether someone is a full or part-time employee. But now that we've made it, we realise that it's really of no use at all. Since each of the values covers about half the entries in the database, it would be quicker just to look through the main entries than to try to use the index. This index might be useful if one of the two rows was much smaller than the other. Perhaps we have a senior staff boolean, and we often want to query according to that value, and there's only a small proportion of the organisation who are considered senior. While this would make the index of some value, note that you'll spend a lot of time maintaining the other half of the list that contains most of the values in the database, and you'll never use it. Later we'll discuss what is nearly always a better way to handle this sort of case. This illustrates the next rule we have for making indexes. We should prefer what are called selective predicates. A selective predicate is one in which most of the entries tend to point to only a small number of records. We will see later, by the way, that I say predicate and not fields because we can have other values in an index than just fields. Look at our index again. If I ask you for all the Adamses and their hire dates, you'll have to look at the index and then go to each Adams entry and look up their hire dates. But if I ask you what branch they work in, you don't even have to go to the main entry. The information you want is actually right in the index. This is called a covering index. They are not universally a good idea because they make the index bigger, so it takes up more memory and disk space. But often you can add columns that you never even search on to an index in order to speed up finding that information. In this case, although this index isn't really useful for searching by branch, it does greatly speed up a search where branch is what we want to find out. So our next rule is to consider adding fields to our index that we don't even search on in order to avoid having to go to the heap for queries that don't need all the fields. This, by the way, is the main reason your mother always told you that select star is usually a bad idea. If you make it a point to only ever select the fields you really need in a query, you give the database itself and whoever is designing the indexes for it the best chance of satisfying what you need from a covering index, which will likely be much faster. It also saves memory in the cache and time shuffling data around that you aren't using. For our next point, we have to abandon the phone book metaphor because it isn't quite like the way a database index actually behaves. So consider the index we showed earlier. Following Gwen's advice, I've made my index of branch and hire date with the date first, because hire date is very selective, whereas branch is not very selective at all. And this is great if I ask you for whoever was hired in the Tampa branch on May 27, 1979. But what happens if I ask you for everyone hired in that branch in the first half of 1979? If you think about what you're doing, if you try to use this index to satisfy that query, the branch column is really only useful insofar as it makes the index a sort of covering one. Otherwise, you have to pretty much just look through all the entries for the date range you're given. Contrast that with the case where we put the branch first. Now you can use both the branch and the date range from the index to satisfy the query. And now we can see the full subtlety of how the database can make use of a compound index. The database can match on the first field, or the first and second, or the first, second, and third, but not the second or third alone. It has to be left to right, well, more or less. In fact, the database might try to use the second and third column, but to do this it has to search through all the entries on the first column, which isn't usually an efficient strategy. As soon as you get to a field with the range condition, we can't look any further into the index. So we need to design our indexes with this behavior in mind. We put the covering fields at the end. In front of that, we put a field we might do range searches on. In front of that, we put fields that we often search on, balancing selectivity with how often we use them. And we consider having multiple compound indexes for various cases we can't cover with just one index, bearing in mind the cost for insertion time with multiple indexes. One last trip back to our phone book while we revisit indexing a Boolean. What we would do in practice with our senior staff search in a real phone book is we would make a special senior staff only index. This is much better and more practical than indexing a Boolean field. We can do the exact same sort of thing in a database by creating what's known as a partial index, which is just an index with a where condition. It is important to note that the database is not super smart about noting when it can use such an index. You mostly have to explicitly and exactly include the same condition used in the where clause of the index. The database will notice range overlaps. So if your index has a date range where condition, higher date is after 1990 or something, then the database will consider that index if your where condition is within the range of the index, even if not identical. Your database might also know that an actual value matches a not null index where clause, but you should test that whether that is so in your database. If your where conditions are not picking up the index in your query, then you need to do as illustrated in this example and exactly include the index's where condition, even if it is redundant with other parts of your query. Another thing we can do in most databases is to index not the value of a field, but the value of a function of one or more fields. So if you want to do case-insensitive text comparisons, you can create an index on the lowercase form of the field. And if your search uses the same expression as in this example, you can use the index without cluttering up the table with denormalized fields. Note that the same sort of caveat applies here as to the partial index case. You have to use the same expression in your query as the index uses. You couldn't, for example, use this index to match against the uppercase form of the field, even though you can see that the database could actually use the index if it was very clever about it. It isn't though, and it won't, if you see what I mean. We see now why I've been speaking of predicates rather than fields in indexes, as predicate is the broader term that encompasses both fields and functions of fields. Another case worth discussing is using an index to match a like condition. You can see that you can use the index to resolve a begins with like condition, and your database can do the same thing. But if I ask you to use this index to solve an ends with query, you can't. You can use a full text index to accelerate like searches more generally, but those are very big and very slow to maintain. A neat trick illustrates how you can use these indexing techniques to sometimes find a clever solution to a problem. In this case, if we want to accelerate searches for the ends of strings, we can index the reverse form of the string and the search string. And now we can find all our streets with ease. We can use an index for sorting whenever we have the same predicates in the index, the query, and the order by. We can sort on multiple fields this way and in either direction, but not in different directions at once. In Postgres, which is the only database that supports this, you can choose where nulls go in the index order. Related to sorting is query using limit or fetch first or the like, where you only need some subset of a sorted list. Paginating is an obvious example. You'll only be able to do this if you're using an index or if you can sort on the index, and even then you need everything you're doing to support pipelining, meaning being able to get rows one at a time rather than having to gather them all as a single unit. And you have to be able to stop all parts of the row at a time gathering process once you've got all the values you actually need. This is database dependent. Note in particular that Postgres Windows functions don't support pipelining. So if you want the first 10 values of some windowing function over what would be a large data set, Postgres will fetch and process the whole data set before throwing all but the first 10 values away. Another use case. Assume we have a web app and we're doing pagination. We show 50 records on a page, we're on the 20th page, and we want to do a next link. This example will work, but is desperately inefficient. To execute this, the server has to locate and discard the first 1,000 entries before giving you the ones you're after. Even with a nice pipelined index helping us out, this is still doing a lot of work we don't need to bother with. And note that this will get slower and slower the further we get into our result set. You see, we know the values of the 1,000th record because it's on the page the user is looking at. So we can just do a query that jumps straight to it and then gives us the records that come after. Note that the syntax here is the most elegant way to deal with such a query, where we can have a where condition that looks just like our order by. Only Postgres fully supports this row value, as it's called. In other databases, we have to simulate it with the clumsier and less efficient bottom type of expression. And if the higher date field might be null, it gets even less pretty. An often effective but little used technique you may be able to easily employ based on your indexes is what Postgres calls clustering. This is where you have the database physically sort the heap according to an index. When you do this, you reduce, often substantially, the number of disk seeks required to read records from the heap when you're reading in the order on which you clustered it. It just reads continuously through the file. Note that this is a once-off operation, and new records likely won't be in their place in the index. So you might want to cluster periodically, and it will still speed up the operations for the older records in the database. Note that this will lock the table for the duration of the procedure, so you need to be able to tolerate that. An interesting technique that illustrates some use of indexing and clustering, and which can be a powerful alternative to just indexing. This technique is called partitioning. As an example, we can do this in Postgres using its very useful table inheritance feature. This lets a table have child tables, which can have extra columns, and when you query against the parent table, it transparently includes all the child tables. To partition with Postgres, you have an empty parent table and numerous identical child tables, except that each has a different check condition, which means that all records can only belong in one of those tables. We determine which child table to insert into in our application code, or it is possible to have Postgres do this with a rule or trigger, although we won't go into that here. I had someone explain how they used this technique to implement a very fast data logger. They had to keep a large volume of log data on inexpensive hardware, with log entries coming in very fast, thousands of entries a second. They wanted to be able to retain and search the data for the last month. They had a partition per day design, with the most recent partition having no indexes and the others having all sorts of useful indexes. This meant that they could insert at the fast possible speed into the today partition, but could still search the other partitions very quickly. At the end of the day, they dropped the oldest day's partition and clustered the current day into a new index day partition. A useful technique in this case is to put the new day table on a separate drive, since then the database can write to the new day partition and read from the historical partitions simultaneously. In the limit, you could maybe have an insert partition on the last hour's values, say, and you could have a very searchable, very fast to insert system indeed. MySQL has an explicit partition command that allows you to achieve a similar effect, and Oracle and SQL Server have, of course, all sorts of complex ways of doing this as well. I know I went through all of that very quickly, but if you're interested, the Postgres, SQL Server, and MySQL websites all have nicely written discussions of how to do it. And the Oracle website has an overlong, complex, and hard to follow one. All of this discussion we've only dealt with searching on a single table. Of course, very often we want to speed up queries involving joins. This is the subject that in my experience most developers are unclear about. The prevailing wisdom is that one should index foreign and primary keys and the other fields we're interested in searching on, and we're done. As we'll see, this is very often quite wrong. There are three ways for the database to do a join. The simplest, default way, and the only way available in MySQL, is the nested loop. A nested loop is how you're tempted to do the join in your application code. Find all the records on one side of the join and then query one by one for the matching records on the other side. The database will often do this very thing just as painfully, and it only works faster than your application can do it because it all happens in the database. Another common strategy is to suck all the values from one side into an in-memory hash table, which saves the index or table crawling in a loop that the first strategy requires. This is called a hash join, and note that it is available in the MariaDB fork of MySQL. Finally, there is the merge join, which is when we sort of zip together two sorted lists. The nested loop join is what I think developers have in mind when they just index the join predicates and the other search predicates on both sides, and you use this obvious naive indexing strategy for this case. Things are quite different with a hash join. This is only for joins on equality. You can do more esoteric sorts of joins on ranges in in which case you're probably stuck with a nested loop. In a hash join, the database builds an in-memory indexed form of the results from one of the tables, so indexing on the join field on that table is completely pointless. It just won't get used, and unless it is used in some other query, it's wasting time and space and should be dropped. I know, not indexing a foreign key feels a little unclean, but you'll get used to it, especially when you test how things behave without it and everything's fine. For a hash join, to speed up the query, you should index for the non-join predicates, and you should try to keep the hash table as small as you can, so that it doesn't intrude on otherwise useful cache, and so in particular the server doesn't start hitting virtual memory. Make sure you only select fields you really need, and if you can find other where conditions that can exclude rows you know won't be in the join, even if they're implied by the join, you should do that. A merge join is not very often used because in general a separate sort step would be expensive. It is useful for outer joins though, and it is useful if an index can give us the values in an already sorted order. This will happen if you include the same fields in the index, the where condition and the order by. Note again that there is no point indexing the join field. And again, this is all done in memory, so anything you can do to reduce the size of the results on either side will help. I would now like to speak briefly about the possible index data structures. The main index types are B-tree and hash. A B-tree is the most common type because it works well for both comparison and range searches. A hash index should be a bit faster for the case where you really only want equality comparison, particularly for a foreign or primary key, but I would be inclined to test how much advantage there was in using it, given that you are abandoning doing efficient range searches if you adopt it. Postgres offers some other choices with some data types, particularly with extensions and libraries such as PostGIS and full text indexing. GIST is a fast and compact type of index. In some cases, a variant of it called SPGIST will be faster. I would not worry about this unless you are using a library or plugin that advised you to use it. GIN is useful for many of the same purposes as GIST, but it trades a lot more insert time and space for a significantly faster search time. Note that this trade-off is available to you when using full text indexing in Postgres. I would advise you to test and use your best wisdom. I'd like to point out, by the way, that full text indexing in Postgres is surprisingly capable, offering stemming and most of the other most important features that you might be tempted to use something like Lucene for. For most users, Postgres' full text indexing is all you need. There is an important point to be made about query plan caching. As I mentioned at the beginning, searching for a good query plan is difficult. Servers must use a good enough approximation in many cases, and even then, query optimization can take up substantial time. MySQL is particularly prone to a problem with this issue. I've more than once given MySQL a complex query and seen it take 30 seconds to optimize the query before taking a fraction of a second to actually execute it, although I believe it's a bit better about that more recently. In order to mitigate this sort of overhead, SQL Server and Oracle will cache the query plan whenever you use a bind query, where you put question marks or some such in the query itself and then supply the values that go in those places separately, or when you use a prepared query. This has advantages and disadvantages. Generally, it is a win, but note that it is working out how to solve the query without reference to the actual values we're providing in a particular case. So a search that might be able to use our senior staff index, but that won't be able to do that for most of the database, will never use it if you're using a prepared query. To prevent this caching when you don't want it, you can use a non-prepared query with inline values, don't forget to sanitize them, to persuade the server to do its query plan from scratch. Finally, I'll note a very important thing to bear in mind. The query optimization is based on statistical samples of the tables involved. These samples are by default kept to a relatively small number in order to make the sample taking not be too much of a load. But in the case of uneven distributions, such as our senior staff case perhaps, the normal number of samples may be insufficient. All of the databases support tuning the number of samples gathered. This varies from Postgres, which lets you set this for a single predicate, through to MySQL, which offers you only a single setting for the entire database, which is rather unfortunate. That is plenty for one presentation. There is much I didn't cover here that is relevant. A basic understanding of logic can be very important in both designing a schema and more so in designing queries. You should certainly take the time to learn how to use explain in your database. You should know how to use common table expressions and window functions, as these can simplify both writing queries and executing them. If you're considering using a NoSQL database instead of a SQL database, you should look carefully at Postgres HStore and imminent JSON features that will give you all the benefits you might get from less structured storage without abandoning the many benefits that the relational model brings. You should also know how to tune your database for the hardware it is running on and the types of work that it is doing. There are many more things that also might be said. I've been learning and using databases all my professional life, and I still often learn new tricks and techniques. If you've learned some useful techniques here, I think I can finish by saying that you should attend more to your database and how to use it effectively. It is at the heart of most applications, and it is probably the first place you should look when trying to improve the performance of most applications. Thank you.